So we're going to do a couple of examples here about applying modelling. So as with many things in A-level, we can try and model this situation. So let's give it a read. It says, the price of a car in pounds, this is important because sometimes it's in thousands of pounds or something, X years after purchase. So here what I like to do is I like to think, what does a 0 mean? What does a 1 mean? So one year and duration of 1 year and 1 year after purchase mean the same thing. So you don't need to be careful with this. Sometimes you need to be careful with this. It's given by this function. So 15,000, 0.85 to the power of x minus 1,000 sine x. X has to be greater than 0. Why would this be? Well, x is years, so we can't have negative years. So use the model to find the value to the nearest £100 10 years afterwards. Well, this is why it's helpful to go through and just think about these numbers. So we definitely know that this is x equals 10. I don't think we actually have to do any iterative formulas or anything here, do we? We just, looks like to me we need to plug that number in. So if we plug that number in, there we go, 3,500. So what you do is you write this with lots of decimal places and then you write your final answer afterwards. Next, show that there is a root, right? So finding roots is what the Newton-Raphson process or the iterative process is all about. So show that it has a root. So show that here means we are actually meant to use the 19 and the 20. So this is our question that was like, one of these will be a positive, one of these will be a negative. We're going to write that general statement again. Why do I suggest it's going to be positive than a negative? Well, I'm thinking a little bit about the context. I can see 15,000. It looks to me like maybe this thing might be starting as with a big value, and then I'm expecting the car to get to be worth less and less. But change in sign is really what I'm looking for. So there we go. We show them. We say that there's a change in sign, and then I'm going to critique this and say it also needs to use continuous. So at your own peril, you do not choose to write this word here, okay? I've seen it all the time in papers. So, and it's a continuous function, so it means there's a root. Next, find f of x, f dash of x, sorry. So what's this? Well, I would say that this is a sign that we're being set up here to use the Newton-Raphson process because that needs the derivative. So we need to differentiate our starting our starting piece. So let's have a little think about that. Oops. So the 15,000 I can just leave alone. With integration and differentiation, you can generally leave numbers at the front alone and just put them back later. I need to know how to differentiate. I need to know how to differentiate 0.85 to the x. That's the problem. Okay. So when you differentiate exponentials, the trick I always like to remember is the same again. So the same again means it's the same, and then natural log of the number bit. So that will be the derivative for the first part. Sine, we also now know that sine, so I'm going to do that. And then I'm going to put the 15,000 back. The 15,000 and the natural log of 0.85 are both numbers. So they could go together, but I would just leave it. I'd probably write the 15,000, then I'd write that, then I'd leave that at the end. No, you cannot put that 0.85 with anything else. It's trapped by that power. So you do that, and then the sine bit is going to be minus 1,000, and then just cos x. Okay, so that's going to be what f dash x is. I've accidentally revealed sort of the next part as well, I think, haven't I? Have I revealed it? Yes. So you can see the first statement that I was talking about here. And what are we doing? So we've gone on to part D here. So we're taking 19.5 as our first approximation. So this means that 19.5 is the x0 bit. That's what that means. Apply the Newton-Raphson method. So the Newton-Raphson method is in the formula booklet. And do it just once to obtain a second approximation for when it's 0. This just means that it's about roots, which is what we would normally do anyway. So we can see that when we do that, we get an answer of 19.5. And that makes sense because we knew that there was an answer there was a root between 19 and 20 anyway. Criticize the model with respect to value as this gets older. So as we speak, on a paper from this year, I've seen a question all about this as well. So the classic thing that they like to say is there's two problems, isn't there? So one is that eventually, you see at 20, the car can have a negative value, but we would say that, you know, a negative value, so you could say something like negative value is unrealistic, as it would have scrap value, yeah, or even rise again in price. So they often like to say, like, the car could become a classic car or something like that as it gets older. Let's see what they've gone with. Yeah, so they said you can never have a negative value. I've also seen quite a few times before the idea of a car becoming a classic car and so on. So you just have to get into the model of the situation is the idea. So 10D has quite a few questions. There are some pretty good ones there in the book, but just read them carefully and apply the different strategies. Fundamentally, this is all about roots. I will just say, as a little bit of an extension for you, this was all about when f of x was equal to 0, right? So on some very hard questions I've seen before, you can, in fact, use the Newton-Raphson process to find stationary points. How do you do this? What you would do is you would first have everything differentiated, and then you would be finding roots of this. So this, I've only ever seen this sort of once or twice, but you can in fact do this to find stationary points sometimes as well. It's quite rare, but you would keep this bit the same, wouldn't you? And then you would just sort of, if I just go back so you can see, instead of having it like this, you would have the derivative over the second derivative, and you can use that as a way to help you find when f of x, f dash x is 0, as well as roots. Okay, just an extension there if you wanted it. So modeling for numerical methods.